All right, everyone, good afternoon. It's Thursday, which is really like Friday, right? Got some material to cover here, starting chapter 4 today. So we're done with L'Hopital's rule, all that limit stuff. So we're going to do 4.1, maximum minimum values. At 1:30, I have an alarm set. I've got to give my daughter her pain medication. So that'll take I already have it ready to go. So I just have to give it to her real quick. And then we'll come back. If for some reason she needs me during class, she's going to call me. So I have my phone on just to let y'all know. And then next time we'll be covering 4.2, the mean value theorem. So any questions first over any of the homework, anything you want me to do, any problems you want me to show you? Y'all are good? No quiz today, so I'm hoping you did all your homework, or at least you'll get it done this weekend. Okay, all right, let's get into it then. We are starting chapter 4, and chapter 4 is called Applications of Differentiation. So we finally really get to see the real power of the derivative and what we can do with it, where it's most commonly used. And we've already seen how you can use differentiation when we're doing related rate problems. That's like the balloon. Oh, I see someone wants me to do a problem. I'll look at that in a minute, Nico, hold on. Where you have like a balloon that's being inflated at a certain, rate, how fast is the radius increasing, those word problems, those were applications, but this chapter is dedicated to kind of a different type of application that is very important, throughout a lot of the STEM, curriculum, whether it be computer science or engineering or, even biology, anytime we want to find the highest and lowest points on a function, we're going to be using the information from this chapter. All right. Okay, so I'm being asked about, I guess this is in 3.7 to look at number 24. Oh yeah, okay, yeah, let's look at that real quick. We have the limit as x goes to infinity. Of the square root of x times e to the negative x over 2. That's the way they have that written. So we need to figure out what's happening here as x goes to infinity. And I will just point out that this right here really means e raised to the, you could write that as negative 1/2 in front of x. That's kind of another way you could write that. And that might help us when we're letting x go to infinity. Of course, the square root of x will go to infinity, right? And then we have times, and now we have something that looks like, well, if we plug infinity in here, we take half of infinity, it's still infinity. We multiply by negative, we get a negative infinity. So this is really looking like it's going to like e to the negative infinity. And this goes back to, again, the idea of, do you know what the exponential function looks like, e to the x? So if you look at the function e to the x, which was chapter 3, section 1, I went through it really quickly because this was a review of college algebra, right? This is what e to the x looks like. And when we're saying e to the negative infinity, what we're saying is, if you're looking at this function and you head towards negative infinity, and you're walking along this function, walking this way, how high off the ground are you? Like, what's happening, right? And this function is asymptotically approaching 0, right? It's approaching 0. That clear, everyone? So like e to the negative infinity is headed towards 0 in the limit. So that goes to 0. So we have infinity times 0. And I said, anytime you have infinity times 0, you're going to have to pick one of them and drop it to the bottom, right? So the question becomes, which one do we drop? So I think I'm going to do it this way. I'm going to leave the square root of x on top, and I'm going to drop this e thing to the bottom. So the way I'm going to drop this is I'm going to use the fact that I know that if I have something raised to a negative power, I can rewrite it on the bottom to a positive power. So like, as an example, if I had x to the -2, that's the same as 1 over x squared. So I can rewrite that e to the negative x over 2 as e to the positive x over 2. See, that's me dropping it down. Questions on that? I chose to drop the e because I realized that I'm going to have really not that big of a problem taking the derivative of this. I kind of feel comfortable with the derivative of e to the x over 2. Or you know what, let's do e to the, now it's 1/2 x. Okay, I don't mind taking the derivative of that. And I also don't mind taking derivative of the top. So that's what I'm doing. So I dropped it down. And now I apply L'Hopital because if you let x go to infinity, you'll now get infinity over infinity. We don't have to check that, but that would be what happens if you let x go to infinity. So we can use L'Hopital. Derivative of the top is 1 over 2 root x. We've done that a million times. Now the derivative of e to the 1/2 x is, first of all, itself e to the 1/2 x. Then times the derivative of what was up here, and the derivative of 1/2 x is 1/2. Now, this looks weird, but let's just try real quick to see what happens if we let x go to infinity. Notice on the top right here, if x goes to infinity, you have 1 over infinity. 1 over infinity goes to 0, right? Something fixed on top, the bottom gets big, that thing gets small. So this heads to 0. And then over, now on the bottom, what's happening? You're letting x go to infinity. So this piece right here really looks like e to the infinity, not negative infinity, e to the infinity, which means you're back on this curve, but this time we're headed to infinity, and you're walking along here. And as you walk, you head up to infinity. So the bottom goes to infinity times 1/2, which is still infinity. So the bottom goes to infinity. This is not an indeterminate form anymore. It's not 0 over 0 or infinity over infinity. The way to think about it is the top is really small, right? It's getting smaller and smaller and smaller and smaller and smaller. It's trying to go to 0. And then what you're doing is you're taking that and you're dividing it by this really big number. Well, anytime you take a number and divide it by a big number, it gets smaller, right? So it's kind of like the top wants to be small, and the denominator getting big helps the top get small. So they work together to head to 0. So this goes to 0. Does that help? Any other questions?
In the event that we have like a similar response, do we have to explain all that you say right now, like write it or something? Or
do you have to explain what?
Yeah, so if we have like 0 over infinity, we just deduce it's 0.
That's fine. Yeah, you don't need this part. That part's just for me to explain, to make sure everyone understands that that's not a problem. By the way, while we're talking about it, if it was the other way around, if you had the top headed to infinity and the bottom headed to 0, this would still not be an indeterminate form. We can tell what's happening here because now the top is getting big, right? So imagine a number that's getting bigger and bigger and bigger, and then you're going to divide it by a small number. So anytime you divide a big number by a small number, it gets bigger. If that doesn't make sense to you, just take the number like 1,000 and divide it by 1 over 1,000. 1,000 divided by 1 over 1,000, that's the same as doing 1,000 times the reciprocal of that, which is 1,000. 1,000 times 1,000 is even bigger than it was to begin with. So this would head, this is over big over small, that goes to infinity. It's weird how this class, a lot of this class is about just like your understanding of how numbers work together in fractions, right? Like how that ratio, how they interact with one another, right? If one's getting big and the other one's getting big, you can't really tell what's happening. If they're both headed to zero, you can't really tell what's happening. If one's getting big, the other one's getting small, then you can, right? So there's a lot of these little like subtle nuances of number sense, right? Like just a number sense of what's happening. Okay, we good? Can I move on, or I don't mind looking at anything else? Okay. All right, so we are going to talk about chapter 4 applications. The first section is called 4.1 maximum and minimum values. All right. And I have 11 notes here to go with this topic. Okay. A lot of this is just visualization stuff. But there are some important definitions in here that we need to know. So let's start with our first definition, something called the absolute maximum and absolute minimum value of a function. So here's the definition. I'll try and make this a little bigger for us. Yeah, there we go. Okay, given a curve f defined on some domain D. Okay, so you're given some curve, right? You've got some curve over here, f, right? And it's defined on some domain. So, you know, the domain might be all real numbers, or it might be an interval, might be several intervals, whatever. Let's say we have some function on some domain, and we're given some number c in that domain, all right? Then f of c is called an absolute maximum value of the function f on the domain D if, this is the important thing, f of c is bigger than or equal to f of x for all x in D. Okay, all that's saying is that this point C, if you go to it and go up to that point on that graph, that point is bigger than all other points on the graph. All right. It's the king of the mountain. It's the highest point on the graph. Now, in this picture, that actually is not correct because that's not the highest point on the graph. Let me do this. Do that, something like this. Let me stop the graph. Let me make it start and stop somewhere. Okay, this right here, this point would be the absolute maximum value of the function. All right, because it's the highest point on the graph. On the other hand, the absolute minimum value would be the point that is the lowest point on the graph. I have other graphs for you, all right, but that's the actual definition. I'm going to show you some other pictures in a minute. So we have this new concept that the highest point on a graph is the absolute maximum, the lowest point is the absolute minimum. In either case, whether or not you're looking at an absolute maximum or an absolute minimum, in either case, those points would be called a global max or a global min, or sometimes you'll hear them referred to as the extreme values of f, the extreme top and the extreme bottom, right? The highest and lowest points. So that's our first definition. Now, the second definition is what's called the local maximum and minimum values, not absolute, right? Not absolute maximum, local maximum and minimum. So the difference between these two is subtle, but it's important. So here's the definition. Same thing, you're given some function on some domain, okay? And then we have some point f of c. We will call it a local maximum if that point is bigger than or equal to all other points, and this is the key. This is what makes this different than the previous definition. Notice up here, it said for all x in D, meaning that your point was bigger than all the other points in the function. Here, it says near C, which means that you don't necessarily have to be the highest point on the entire graph. You just have to be the highest point in that little, what we call neighborhood. All right. So I think these ideas are best illustrated with visuals. So let me show you with a visual. I have 4 visualizations of this. maybe. Here we go. My graph's a little too big. Okay, so there's a graph of a function, all right? Take a look at it for a minute. Let's talk about the absolute maximum value and minimum value. So this graph definitely has a highest and lowest point, right? Do y'all see it? All right, were these what you were thinking? Right there, those 2 points. This green point right here is the global maximum. It happens when X is 2. You can kind of see 1, 2, 3, 4, 5. So it happens at 2. And when you plug 2 into this particular function, I have the computer doing it. I haven't given you what the function is. I'm just telling you that when you plug 2 into this function, you get 856. So the absolute maximum of this function is 856. Let me say that again. The absolute maximum of this function is 856. The absolute maximum is always the y value that comes out. Okay, it's the highest value. Now we know it happens at 2, right? It's happening at 2, but the height of the point is 856, and that's the maximum value. On the other hand, the global minimum happens here, and it looks like it's happening at -5 is what you plug in, and what it spits out is this value over here, -4,975. That would be the minimum value. Okay, highest point and lowest points on the graph are your absolute maximum. Is this a pretty straightforward concept in terms of like visual? I mean, there's nothing tricky about this, right? So that's absolute max and min. Now let's talk about the local max and mins, or what's called the local extreme value. So I'm going to take these off. To be a local maximum, you only have to be the highest point or lowest point in that little region or neighborhood. So take a look here. All 3 of these points would be considered local maximums and minimums. So this point right here, this blue point, is called a local minimum because if you just focus your attention to like this little area in here and forget the rest of everything, that would be the lowest point in that little region. Locally, it's the lowest point. Also over here, if you focus your attention just here and forget all this, that point would be a local minimum in that little region. So we have 2 local minimums, right? And then we have, whoa, what's going on? There we go. And then we have this one right here, which if you forget everything else, that would be a local maximum. Now, what about the 2 endpoints, the 2 red endpoints? What do we do with those? Well, when I made this demonstration, I forgot to put it on here. I want you to go back and look at this definition for local maximums and minimums. Okay, look at this right here. If a function is defined on a closed interval, which means it has endpoints, then the endpoints are always considered local maximums or minimums, always. So I forgot to put that in my picture when I put this together. So I do need to include here that this right here would be a local, what do you think? Local max or min? Is that the lowest point in this little area or is it the highest?
Maximum.
Highest.
Be the highest, right? Because you would compare it to the points around it, right? And the only points around it are the points right down here. Those are all below it, right? So that would be a local max. And then this point over here would also be a local max, because if you look at the points around it, which are just the ones below it over here, it's higher than all those points. So what we really have in this picture are 3 local maximums and 2 local minimums. Understand? 3 local max, 2 local mins. And then in terms of global, we have 1 global max and 1 global min. So a global maximum can also be a local maximum. And a global minimum can also be a local minimum. But they're 2 different concepts. right? One of them, you're looking at the whole function. The other one, you're looking in these little neighborhoods or regions. All right, let's look at another example. I'll give you a minute. Let's think about the global stuff first. Okay, let's think about the global. This has a global maximum, yes? Where is it?
X equals 2.
X equals 2, right here.
Yeah.
Is that the highest point on the entire graph?
It is x equals 10, no?
You choose whichever, sorry.
So, Halle, what you identified, this little peak right here, this hilltop, is a local maximum because it is the highest point around here. But see, this point to the right is higher than it, right? And this point on the right, this right endpoint is the highest point on the whole graph, isn't it? Like there's no points bigger than it or taller than it or higher than it, right? So this right endpoint would be our global maximum. And then what about global minimum? Do we have a lowest point? I would say, right, here's our, right about somewhere in here, right? Right there. That would be it. That would be our global minimum. So here are two globals right there. All right, those are our two globals. Now let's talk locals. How many local maximums are there here? How many local maximums do you see?
3.
3, okay. They're going to be what? The 2 endpoints, right? Are local maximums. And then right here at this point, we have a maximum right there. And then minimums, we have 2 local minimums here and here. So here they are. And again, I forgot to put, this is a local max. I'm going to put L max. And then this one right here would also be a local max. Questions? So far, straightforward? Pretty straightforward? Okay. It can be a little tricky, so let's keep paying attention here. What about this one? So what I don't have here, what I need to have is, these are arrows, okay? The arrow at the end of the function implies that it keeps going up forever, all right? So let's talk global first. Do you have a global maximum? Is there a highest point on the graph?
Can it be infinity or?
Okay, you would think maybe infinity because it keeps going up forever, right? Well, the problem is infinity is not a number, okay? So we can't say infinity. I mean, it's good to think that, but you cannot tell me that there is a highest value on this graph. There is no highest value because as soon as you say there's one, I can find one higher because these arrows go up. So there is no global maximum here. No global max. How about a global minimum?
-5.
Yeah, -5 down here, we do have a lowest point on the graph. So let's take a look. We have a global minimum at -5. The value of it is -4,975. That's how low it is. And then no global maximum, no global max because it goes up on both sides forever. So you do not have to have a global maximum and global minimum. You don't have to. I mean, you can think about a function that would do this, right? That function would not have a global max and it would not have a global minimum. It wouldn't have either one. Now, locals, let's talk about locals. For locals on this one, how many local maximums?
3.
Local max?
1.
Just one, right here, right? This is the highest point on top of the hill, right? And locally, it's the highest point. And then we have a lowest point here and a lowest point here. So we have 3 total locals, but we have 1 local max and 2 local minimums. And since we don't have endpoints, right? There aren't endpoints on this graph because it goes forever. Those are the only local extreme values you have. Questions? No? Hmm. What do you think? How about globals? Do we have a global maximum?
We have two of them.
Okay, so I heard someone say we have two of them, right? Well, we actually only have one global maximum value. It happens at two different places, but there's only one highest value, right? The highest value that we get out of this function is whatever is however high those 2 points are, right? The height of those points is our global maximum value. It occurs at two different places, right? So we won't say we have two global maximums. We only have one global maximum value. It just occurs at two different x values. How about global minimum? Same thing, right? One global minimum value, but it happens at two different places, right? So it's happening here and here. So at this x and that x right there. But the value, there's only one minimum value. So here's your global. The global maximum that happens at -5, the value is 225. That's this one. The global maximum at 5 has the same value, 225. So the global maximum value is 225. The global minimum value is -64. Don't worry about how I got these numbers. The numbers are just for this specific function, which I haven't even told you what the function is. So that's our global information. Now, what about local? How many locals do we have total? Both max and mins together. How many would we have here?
5.
5, right? 5, here they are. Local max, right? Local max, local min, local max, local min, local max. Those are all our locals. Okay. All right. So I have one for you to think about. We've got something here before we get to the next note. I'm going to draw you a function. I want you to think about it. Okay. So let's say that this is 1, 2, 3. Now I'm going to draw you the function. Ready? Here's the left endpoint. Here's the right endpoint. That's the function f. I want you to think about global max, global min, local max, local min. This is weird, right? This is like an extreme case. Oh, that's the alarm. Let me go give my daughter her medicine while y'all think about that. All right, be right back. Okay, sorry about that. Or maybe she's trying to ask me how long it's going to be before she can feel her mouth again. I'm like, I don't know. Okay, what do y'all think here? This is a little confusing, right? Because global maximum means you're the highest point on the function, right? That's your highest value. Now, if we look at the definition, there's something very important with the definition. To be an absolute maximum, you must be, the point must be what? Greater than or what? Equal to. Greater than or equal to the points around it. And then to be a minimum, you must be less than or equal to all the points around it. So when you look at this, let's say I just pick this point right here, right? Whatever this X value is, who cares? It spits out the number 2, right? So the value of the function here is 2. And isn't that 2 bigger than or equal to every other point on that graph? It is, right? 2 is bigger than or equal to every other point on the graph. But 2 is also less than or equal to every other point on that graph, which means that 2 is both the global max and the global minimum, which is strange. This would only happen if you had a horizontal line, okay? It only works for a horizontal line. I'm just trying to illustrate to you the definition. By definition, 2 is both the global max and the global min. And every point on here is a local max and a local min as well. You could pick, give me any point, I don't care where it is. Any point on here would be a local max, local min, because it's higher than or equal to every other point or lower than or equal to every point. This is an extreme case. I just wanted you to think about it, because initially when you look at that, you'd be like, well, it doesn't have a global max because, you know, it doesn't have a highest point. Well, every point is the highest point and every point is the lowest point. So it's kind of weird. All right, we good? We're gonna move on. So we have these 2 definitions now, right? We've looked at the visual idea behind them. And now we have our first theorem of the section, which is called the extreme value theorem. Here's what it says. If f is a continuous function, do y'all remember what continuous meant? What's the basic idea of a continuous function?
Keeps going.
Keeps going. Yeah. What do you mean?
There's no discontinuity.
There's no
No
discontinuity.
jumps or
No jumps. No breaks. Right.
No corners or cuts.
You can have corners or cuts. That's where it's not differentiable. Right. Okay. That's okay. Continuity means you can draw it without picking up your pencil. Okay. That's what continuity is. You draw it without picking up your pencil. So this says, okay, say we have a continuous function, a function that we can draw without picking up our pencil, and it's defined on a closed interval. All right, let's say we start with that. That means I would have, it being defined on a closed interval means that when I draw it, it would have to start somewhere, right? And then it would have to end somewhere. And then I would have to connect these 2 dots together with something without me picking up my pencil, right? So I'd have to connect these together, however I connect them together. That would be what we're talking about. Now, remember, it has to be a function, right? So you can't do any crazy shit like this because that would fail the vertical line test. So as long as you have a function like that between 2 points, then this theorem applies, right? So this first part is what we're given, okay? We're starting with this. If we're given this situation, then here's the conclusion of the theorem. The theorem says, then the function f attains both an absolute maximum value and an absolute minimum value in the interval. So this theorem is just saying that, look, if you've got a function that's connecting 2 points together and you can't pick up your pencil, then I promise you, it will have a global max and a global min. It must. The existence of those two things has to be there. So I'm going to show you an example here. So do y'all see these 2 points here? All right, y'all see them? What I'm going to do is I'm going to connect those two with a continuous curve. Here we go. Boom, I've connected them, right? That's continuous. According to this theorem, this must have an absolute max and an absolute minimum. There they are. This is the absolute max. That's the absolute min. Do you agree? The theorem said we had to have it, like we would have to have it. There's no way to not have it. Let me give you another example. Same two endpoints, okay? Connect them together. Is this a continuous curve? Draw without picking up my pencil. Okay, so the theorem applies. I have to have global max and global min. There they are. Global max, global min. How about this one? Straight line. Straight line is continuous, right? The theorem says I must have a global max and a global min. There they are, the two endpoints. That's your global max, that's your global min. Now, why is it so important to have the continuity in this theorem, right? Why is it so important? Let's see. How about this? Look at this function I'm about to draw. What I did is I drew a function that has a vertical asymptote. You see that vertical asymptote? Goes up forever. Does the theorem apply here? No, right? This is not a continuous function, is it? You cannot draw from this point to this point without picking up your pencil. And it doesn't, in this case, it does not have a global maximum because look, this arrow means this keeps going up forever, which means you would not have a highest point. So the theorem says as long as it's continuous and you connect two endpoints together, boom, you have to have it. You have to. Questions there? Okay, sure. Next theorem. Now this one confuses students, all right? So if you're confused, just hang tight because we have two versions of this theorem. We have a first version and then we have a second version. The second version is the one that we're going to use and the one that most students can make sense out of. But we're going to look at the first one, all right? I didn't state this before, and maybe I did in the past. Do y'all understand what a theorem is? A theorem is like a mathematical truth, okay? So it's a statement that has been proven to be true. So when I told you here, this extreme value theorem, mathematicians have proven that if you have a continuous function on a closed interval, if that's true, we have proven that this must happen. So all theorems come in that form. There's a given, the given information, and then the conclusion if you have that given information. That's what a theorem is. And the fact that it's been proven before, right? So sometimes proofs are easy, sometimes proofs are hard. If you're a math major, you have to go prove all these things. Like if you're a math major, you're going to go back to calculus and you're going to prove all the theorems that we used in calculus, but you're going to prove them using rigorous mathematical logic, which we don't do here. We just accept the theorems on faith. Okay, so here's Fermat's theorem. Have y'all heard of Fermat's theorem before? Have y'all heard of Fermat's last theorem? No? Okay. If you have heard of Fermat's last theorem, if you have, this is not it. Okay, he had another theorem. So here's the theorem. If, okay, so most theorems have an if statement, and then you have the conclusion. So here's what we're given. If f has a local maximum or minimum at a point, okay? So if we're looking at a function that has a local maximum or minimum at some point, can you visualize that? we've got a graph. Let's just say that at some point I tell you here on the graph, let's go with, let's say I tell you that's a local maximum, okay? I tell you that's a local maximum. Can you visualize kind of what the graph looks like around that? That point should be higher than or equal to all the points around it, right? So the theorem says, let's say we have that, okay? That's the first thing. And this is so critical. And the derivative exists at that point. What does it mean for me to say the derivative exists? And you know what, Ash just brought this up a second ago. There are places where derivatives don't exist. Derivatives don't exist where? Where do derivatives fail to exist?
Cusps and corners,
Cusps and corners,
asymptotes,
asymptotes,
and
Jump.
open points.
and breaks, jumps, right? Anytime you have jumps or breaks in your graph, you can't be differentiable there. If you have a cusp or a corner, you can't be differentiable there. If you have an asymptote there, you can't have it. You can't have your derivative exist. So it's saying here that our derivative must exist here. All right. So we've got a local max here and our derivative exists. The conclusion is that the derivative there must be zero then. Meaning that the slope of the tangent line at that point must be zero. So, that means the graph probably looks something like this, right? Right, that's probably what it looks like. It's a local maximum, so that point's higher than all the other ones. And the derivative exists here, which means we don't have a cusp or a corner, and there's no breaks or jumps, so it's going to have to look like the top of a hill. You have to be careful with this. Let me show you an example that wouldn't work. What if I told you at some point C, right here, I told you we had a local max, right? But let's say I remove this condition here, that the derivative exists. Then couldn't we have this picture? Couldn't I have a cusp there? Wouldn't that still be a local maximum? That would still be the highest point around there, right? But is the derivative zero there? No, the derivative doesn't exist. So you have to be careful with this theorem. This theorem says if you have a local maximum or minimum and the derivative exists, which means you don't have a cusp or a vertical tangent or a break, then we can guarantee that the derivative is zero. Now, like I said, if that's confusing, that's okay, just hang tight. We're about to have something else, all right? So I have a little bit more visual for you. So here's an example here. Notice on this curve, at this point, this is a local maximum, right? Local maximum. And the derivative exists because it's not a cusp or a corner or a jump or a vertical tangent. So the derivative here is zero. You can see the slope of tangent line. This is a local minimum. This should say min, not max. That's a typo. This is a local minimum. And the derivative here exists because there's no cusp or corner. So the derivative must be zero. You can see it's flat, right? Tangent line is flat. Here's an example that doesn't work. There you go. This point is a local max, right? It's a local max, but the derivative doesn't exist here. So we can't, what I'm trying to say is, just because I tell you you have a local maximum is not enough for you to say, oh, then the derivative has to be zero. Just because you have a local maximum, the derivative doesn't have to be zero. But if I tell you you have a local maximum and that the derivative exists, then you can say that the derivative must be zero. Here's another example which doesn't work. What's wrong with this one? This isn't a local max or min, right? Now, is the derivative zero here? Yeah, but it's not a local max or min, is it? The theorem only says if we're looking at a local max or min and the derivative exists, then the derivative must be 0. I want to state this again because this is where students really can get things mixed up. When you have a statement like this is going to turn, I'm going to give you a little short logic lesson here. When you have a mathematical theorem or something of this form where you say, if this, whatever, then here's your conclusion. When you read that theorem, you can only read it in that order. You cannot change the order on your own. Let me give you an example. Let's say I tell you this. If you live in Texas, then you live in the United States. Do you agree with that? Would you consider that to be a true statement? If you live in Texas, then you must live in the United States. Yes? Can I switch the order of that and it still be true? If you live in the US, then you live in Texas. Well, you could, right? You could live in the US and live in Texas. You could, but it's not guaranteed, right? So this would not be true. In other words, you cannot change the order of things. So look, you can't do this. You can't say, hey, look, if the derivative is 0, right? If the derivative is 0, then you have a max or a local max or min. You can't say that. That's not what the theorem says. The theorem says if you have a max or min and the derivative exists, then you can say the derivative is 0. Don't reverse it. You're not allowed to. Logic is weird. Logic is really weird. I don't want to go off too far on logic, but I'll kind of give you an example that when I was first learning logic, this example kind of was like made me scratch my head a little bit. So I'm going to make a statement, okay? And you tell me whether or not you think this statement is true or false. And I should probably preface this with the idea that in our logical system, okay, our system of logic that we use in mathematics, computer science, there is what is called the law of the excluded middle, which means that there's only two possibilities of a statement. It's either true or false. You can't have a statement that's both true and false. It's got to be true or false. There's no third option, all right? So here's the statement. You tell me if this is true or false. All the pink elephants in my room here have wings. I'm sitting in my office right now. All the pink elephants in this room have wings. True or false?
False,
False, why?
because there is no pink elephant.
Okay, that seems to be a pretty strong argument, right?
I want to say true
Okay, why would you say true?
because the question isn't if there are pink elephants in your office. The statement isn't if there are pink elephants in your office. It's there are pink elephants and they all have wings.
All the pink elephants in my room have wings, right?
I would say
It's not up to me to, so Shams said, well, there's no pink elephants, so this can't be true. In our logical system, okay, the way the statement is presented, it's not my task to produce the pink elephant with wings. It's your task to prove there's not one, that you need to find a pink elephant in my room right now that doesn't have wings. Then you can prove this to be false. You must find a pink elephant in my room without wings. If you find a blue elephant, that doesn't do anything because I'm saying all pink elephants have wings. So you've got to find a pink elephant in this room that doesn't have wings, which you're not going to be able to do. This is a true statement, and it is referred to as a statement that is called vacuously true, meaning that it's basically impossible to show it's false. And there's a lot of things in our mathematical systems that works this way. Here's another one. Let's say we're talking about real numbers only right now. Okay, real numbers. If I say this, if x squared is less than 0, then Robert is the king of the world. Robert referring to me. Is that true? If x squared is less than 0, then Robert is king of the world. Yes, I am the king of the world. Okay. The reason I'm the king of the world is because your initial assumption is false. If you're talking about real numbers, there's no way you can square a real number and get a number smaller than 0. You cannot do that because then it would have to be negative, right? So in other words, your assumption, right? What we assumed in the beginning, our assumption is false. If you start a statement with a false assumption, your conclusion is always true. All right, look, I'm showing this to you because this is the way our logic system works, okay? This is the way logic works. If you don't like it, don't like it. This is the system we use, okay? It's got weird shit in it when you start to look at it. Not that it's wrong, it's weird. Because anytime you start something with a false assumption, the conclusion you draw from that will always be true. It's weird. Okay, I think I need to stop. I could talk all day about logic, but we're not going to. All right, so there's the theorem. Okay, and I told you, let's not get too bogged down on this, okay, because we're going to rephrase it here in a minute. That's going to be useful to us. So I need to do one more thing before I can do that. I need a new definition. And you should put several stars next to this definition, because this is, in this section, this is one of the most important concepts of the section, is what is a critical number of a function? Okay, what is a critical number? Well, they're critical, right? They give them the name critical because they're freaking important, all right? They're important for something we're trying to achieve. All right, so critical numbers, here we go. A critical number of a function is some number c in the domain of the function such that one of these two things is true. All right, so a critical number of a function is some number that is in the domain of the original function, which means you're allowed to plug it into the function. And we will call it a critical number if, when you plug that number into the derivative, you either get 0 or the derivative doesn't exist at that number. Anytime you have that happen, that number c is called a critical number. All right. Anywhere, so if you wanted to really kind of like real fast explain what a critical number is, you could just say a critical number is anywhere that the function's derivative is 0 or the derivative doesn't exist. You just have to remember that the number you're talking about better be in the domain of the original function. It has to be. If it's not, then it's not a critical number. Now, why are critical numbers important? Why do we want to know about them? What role do they play? Well, look at the theorem, the next theorem, and the one that's important. This is the big one right here. Here's the theorem. If f has a local maximum or minimum at a point c, if it does, then c is a critical number of f. Why is that not highlighting? If your function has a maximum or minimum at a point, if it does, then I promise you that that point had to be a critical number. if my function, if it has a local max or min at some point, then the point that it has the max and min at has to be a critical number, which means it has to be somewhere where the derivative is 0 or doesn't exist. So that means that if I ever want to find the local maxes and mins of a function, I should probably go find the critical numbers, right? If I can find the critical numbers, then I can at least try to identify where the local max and mins are. All right, so let's do it. This last piece here is the biggest note of the section right here. If you're going to take one thing away from this, right? If you're just sitting there kind of like daydreaming this whole time, if you're going to take one thing away, it's this final note. This is how to find the absolute maximum minimum of a function on a closed interval. Okay, so if I give you a function on a closed interval, how do you find its highest and lowest points? This is referred to as the closed interval method. So here it is. Here's what we're going to do. To find the absolute maximum minimum values of a continuous function on a closed interval a, b, here's what we do. First thing we're going to do is we're going to find the critical numbers of the function. Okay, so we're going to figure out where the derivative is 0 and where the derivative doesn't exist. We're just going to go figure out where that happens. Once we figure out where that happens, we are going to evaluate the original function at the critical numbers. After we do that, we're going to evaluate the function at the endpoints of the interval. And then last, we're going to compare the answers we got in steps 1 and 2. And whatever the biggest value we got out is our absolute max, and whatever the smallest is our absolute min. Those are the steps. I'll copy them here. Let's go do an example. Before I do this, real quick preview, all right? What we're really doing in this section, the main two topics in this section are this. If I give you a function on a closed interval like this, okay, on a closed interval, and it's continuous, you are going, let me redraw it like that, okay. If I give you that, one of the goals of this section is for you to be able to find the highest and lowest points on that graph, all right? That's the first thing we're doing. That's what I'm about to do right now. The next thing we're going to do, not the next section, but the section after that, is what we do is we say, forget that it's on a closed interval. Just let it be, let the function, not have to be on a closed interval. Can we still find these highest and lowest points? Can we still do it? And so that right now to us is an open question. We don't know how to do that yet. This is what we're doing today. That's why it's called the closed interval method, because it's how you deal with a function on a closed interval. This on the right-hand side would be like what you consider like an open interval method, but we'll get to it later. All right, so let's go. Let's do it. Example, first example of this. Find the absolute, I'm just going to put abs max and the abs absolute or extreme, whatever you want to say there. No, I'll put abs for absolute. Minimum of f of x equals x to the 4th minus 9x squared on the interval 1, 3. Let's make it -1, 3. So we have this function, right? And I want to know between 1 and 3, if you were to draw me that function, what's the highest value you're going to get out and what's the lowest value you're going to get out? Okay, that's what I want to know. So we are going to use this method because we have a function, right? This function is continuous. How do I know that that's a continuous function? How do I know that this right here is a continuous function? Boy, I'd have to go way back in my notes for this. When did we cover continuity? Let's see here. Yeah, not. Let me see. Let me go back to my calendar. When did we cover continuity? Oh, where is it? Oh, continuity 1.5, way back there. 1.5, which should have been around January 25th. Let's see.
We covered it right before the first exam.
Yeah,
Oh, yeah, also we're behind the calendar, so it might.
yeah, I think we're a little bit behind here. So this is limits. Give me a second. Give me a second. Geez, you know what? It's probably more efficient if I just do it this way. I'm just going to go back to our actual notes. Okay. How do we, the question is, how do we know that that's a continuous function, right? That's what I'm asking you. How do we know that? So I'm going to bring up our chapter 1 notes. And I'm going to go to continuity. Okay, we covered these notes. And then way at the bottom here, after I describe what continuity is and all this. Here we go. Theorem. Functions which are continuous. All polynomial functions are continuous. All rational functions are continuous on their domains. All trig functions are continuous on their implied domains. All exponential and log functions are continuous on their implied domains. So, why is this continuous? Because this is a polynomial, right? It's a polynomial, so I know it's a continuous function. We have to have a continuous function for this theorem to work, or for this method to work, which I have. So I'm happy about that, okay? So first thing I'm going to do is I'm going to find the critical numbers. All right, so what are the critical numbers? Well, it's anywhere where the derivative is 0, right? Or anywhere that the derivative doesn't exist. So here's what I need to figure out. Where is the derivative? Where is the derivative equal to 0? That's a question. And the other thing I need to look at is where is the derivative not exist? Okay, where does not exist? Right, those are the two things I want to look at for critical numbers. Well, that means I need the derivative, right? I need to be able to take the derivative. So what is the derivative of x to the 4th minus 9x squared?
4x to the 3rd minus
4x to the 3rd minus
18x.
18x. And I want to know where that's 0, right? And then I also want to know where 4x to the 3rd minus 18x. The question here is, does this ever not exist, right? So let's start with the first one. There's my derivative, and I need to set it equal to 0. Do you remember me a long time ago when we were taking derivatives? I was saying, hey, we're just doing like raw derivative. But eventually, at some point, you're going to have to set these things equal to 0 and solve. Do you remember me telling you that? Like at some point, we're going to have to do algebra with this derivative and clean it up. Today's the day, all right? We now need to do something with the derivative. So I'm going to take this derivative, and I'm going to set it equal to 0. Okay, here we go. I'm going to factor. I can pull a 2x out of both of those. When I do that, I'm left with a 2x squared minus 9. Y'all with me? Yeah. Pull a 2, pull an x out of both. Let's set both of these equal to 0. 2x equals 0. Let me set the other one equal to 0. 2x squared minus 9 equals 0. This one, the only answer is 0. And then here, well, that I'm going to have to move the 9 to the other side. I'm going to have to divide both sides by 2. And then I'm going to have to take the square root on both sides. And then because I'm taking the square root, I have to do plus or minus 9 over 2, square root of 9 over 2. Which I think I'll get my calculator to do that. I'm going to get a decimal for that. So on my calculator, I'm just going to do 9 divided by 2. And then I'm going to take the square root of that. And this is approximately x equals plus or minus 2.12. I have three answers for where the derivative is 0. All right. Don't forget though, I also need to know where the derivative doesn't exist. So look at this derivative. Are there any values of x you cannot plug in? Like, are you ever going to plug in an x and get like division by 0 or the square root of a negative number? Is there anything that's going to go wrong if you plug an x into this ever? It's a polynomial still, isn't it? I mean, this is a very, very well-behaved function. I can never feed that a number and it can't handle it. I can cube any number and I can multiply any number by negative 18 and there's no problems, right? The things I'd be concerned about if I had like a fraction with x on the bottom, or if I had a square root, I'd be concerned, oh wait, what if I plug in something that makes the bottom 0? So this right here, there is no issues here, no issues, right? No issues with the derivative ever not existing. Y'all still with me? I have three critical numbers. Here's what they are. X is, I'm just going to list them out. 0, negative 2.12, and 2.12. I'm going to throw away this one. Why? Somebody tell me why I just threw that one away.
Not in the domain.
Where was I asking you to look? I said, let's find the absolute max and min of this function, right? On -1 to 3. So your critical numbers that you find have to live in here. If they live somewhere else, you're not gonna concern yourself with them. So if I'm only looking between -1 and 3, well, yeah, 0 lives there, right? 2.12 lives there, but see, it stops at -1 left. This one does not live there, right? So I'm not going to include it. All right, so step one of this method, find the critical numbers. Have we done that? Have we found the critical numbers? We have, right? There was 2 of them, 0 and 2.12, right? So I found the critical numbers. Now what do? Evaluate the original function at those critical numbers. That means I want to take those numbers and plug them into the original function. This is still part of step 1. So now what I'm going to do is I'm going to take the original function, I'm going to plug in 0. I'm going to take the original function, I'm going to plug in 2.12. And the original function was up here. So let me just copy it real quick. I'm just going to slap it down here so we can see it. Right, that's the original function. So when I plug in 0, I think that's easy, right? Plug 0 into this, you just get 0. But if I plug 2.12 in, I have to do 2.12 squared minus 9 times to the 4th, minus 9 times 2.12 squared. Calculator time. Now would be a good time to ask a question if you have one. For those of you who are playing along at home, negative 20.25-ish, something like that. Anybody else get that? I hope. Yes, no. All right, hang tight. Let's see where we're going with this. We found the critical numbers, right? and we evaluated our function at those critical numbers. Step 1's done. Step 2, evaluate the function again, but at the endpoints of the interval. So for step 2, what I'm going to do, step 2, is I'm going to evaluate the original function at the 2 endpoints. What were our 2 endpoints? Negative 1 and 3, right? So I'm going to have to plug in -1 into the original function and 3. So let me do that. That's -1 to the 4th minus 9 times -1 squared. And then I'm going to have to do 3 to the 4th minus 9 times 3 squared. All right, this one I should be able to do. -1 to the 4th power is 1. And then -1 squared is 1, then times -9. So -9 or minus 9. So you get -8 there. And if I plug in 3 to the 4th, that's 81 minus 9 times 9. Hey, wait, is that 0 again? I got 0 again. How is this? Step 2 is done. What do we do now? Let's see. Now we are going to compare the answers we just got from 1 and 2. The largest is the absolute max, the smallest is the absolute minimum. Which means, let me see if I look at these. What's the largest number I get? I'm looking at just the numbers I got here, 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 and here. What's the biggest number I have?
The -8.
Careful.
Oh, no,
0.
0, sorry.
0.
0, right? 0 is the biggest number there, right? So I have an absolute maximum value of 0, right? It actually happens at 2 places, doesn't it? When you plug 0 into the function, you get 0, but when you plug in 3, you also get 0, right? But the absolute maximum value is 0. And then what's the absolute minimum?
-20, 25.
Yep. -20.25. And that occurs when I plug in 2.12 into the function, right? We're done. We just found the highest and lowest points of this graph on that interval. That's our answer. We're done. So let's do something. Let's go to Desmos. Let's graph the function. X to the 4th minus 9x squared, right? There's the graph. But I'm only going to look at this graph from -1 to 3. Okay, there, I'm only looking at that graph from -1 to 3. Okay. At -1, when we plug -1 into the function, what did we get when we plugged in -1? Didn't we get -8? Didn't we get -8?
Yes.
Okay, that was that left endpoint. Then when we plugged in 3, we got 0, didn't we? That's that right endpoint. And then we found our critical numbers, which were 0. When we plugged in 0, we got 0. That was this point. And then we found another critical number, which was 2.12. And we plugged that in, we got -20.25, which is this point right here. Right? That's what we just did. We found, what we did is we used the derivative. We used the derivative to find these 2 points. We weren't sure if those were the biggest or smallest. We couldn't really tell, but we knew that if there was any other point that would maybe beat those, it would have to be an endpoint. So then we would just check and compare them to the endpoints. And we said, hey, looking at all of those together, the biggest value we see out is 0, right? And the smallest we see out is the -20.25. You can do that for any function. so long as you can take the derivative, set it equal to 0, also look at where it doesn't exist, and you do this technique, and you can always find the highest and lowest points on a graph that way for a function on a closed interval. I started with an easy function because, you know, taking the derivative of that function was simple, right? Well, I hope, yes. Okay, so I only have 23 more minutes, and I have 2 more things I want to do. All right, let's see if this blows your mind or not. I'm getting a little ahead of myself here, but I think I'm ready to show this to you. Let's go back to college algebra. That's a quadratic function in college algebra, right? And when you're taught about quadratic functions, you're told that, you know, this is either a parabola that opens up or it's a parabola that opens down. It just depends on A, right? If A is positive, it opens up. If A is negative, it opens down, right? You're taught that. And you're also taught that all parabolas have a point on them that is either the lowest point on the graph or the highest point on the graph, right? And we call that do y'all remember that point?
Vertex.
Vertex, right, good. So that's called the vertex of the parabola. And it's such an important point that we actually give it a special set of coordinates. Instead of calling the coordinates of that point XY, we call it HK, just so you know I'm talking about a vertex. Does that look familiar, HK? Do you remember this? In college algebra, you're taught how to get H. You're taught H will always be negative B over 2A. Does that look familiar to you at all? Do I remember seeing that? Like if you want to find the H for this vertex, all you do is take negative B and divide it by 2 times A. Yeah, y'all kind of remember that? All right, check this shit out. Forget all this. Forget all that. You're now in calculus. And I'm asking you to try and go and find me the highest or lowest point on this graph. Well, you're going to need to know the critical numbers, aren't you? Which means you're going to need to take the derivative of this. So think about what the derivative of that function would be. What's the derivative? Remember, A, B, and C are just constants, right? They're just numbers. So they're going to come along for the ride. So what would be the derivative of A times X squared?
2ax.
2ax, right? The 2 would come down with the A and it would become 2ax. Plus, what's the derivative of bx?
B.
Just b, right? Because the x goes to 1, the b comes for the ride. And then the derivative of c, it's gone, right? Because it's constant. So there's my derivative, right? Critical numbers, I need to set that equal to 0, right? Take that and set it equal to 0. If I take 2ax plus b and set it equal to 0, this is where I will have a critical number, right? Solve that for x. Solve for x. So what are you going to do first? Subtract b on both sides. And then divide both sides by 2a. And you get negative b over 2a. This is where we should have a local max or min. And that's why in college algebra, we give that to college algebra students as a gift from calculus. We say, here you go. You want to go find a vertex? There you go. That's going to find it for you. All right. But it's just a simple application of what we're doing right now. You take the derivative, set it to 0. Take the derivative, set it to 0. Now you also have to check where it doesn't exist. Okay, good. I just want to show you that because that's really kind of a cool, like, it's nice to see where these formulas come from. Like, oh yeah, I remember seeing that. Oh yeah, here's where it is. Here's where you can show it now. All right, it's unfortunate I don't have enough time. I would really like to do a lot of examples right now. I'm gonna just like throw you to the frying pan and I'm gonna have you try and do the homework for this. Because there's nothing new for me to do for you you have the technique to find the absolute max and min. You take the derivative, you set it equal to 0, you see where it doesn't exist. You plug those answers into the original function, you compare the endpoints. We can do more practice. And you know what, next class we can do more. I want you to try to do your homework. Watch the homework solution videos to help you if you're having trouble with it. And you will run into issues because some of these functions are just nasty, okay? When you start taking derivatives and setting them to 0. So do what you can on the 4.1 homework, but we will come back and do some more examples. I really wanted to do a certain problem to end class today. This one. So I offered this as a bonus problem at the beginning of the semester. Very beginning of the semester, I offered this as a bonus question. And I said, okay, we're trying to run, we have a river separate, a 500-foot river that separates two buildings, buildings A and B. Building A is 2,000 feet downstream or upstream from building B. And our company wants to install fiber optic cable that connects these two businesses together. And you're told that the company knows that it will cost about $470 per linear foot to install the cable below dry ground and $710 per linear foot to install the cable underwater. So, how should you proceed in order to come up with a competitive bid? So it's like your company knows how much it's going to cost to do this, right? So let's say we are the company who wants to, do this job. So we have to propose a bid to the people who want us to do this, and we want our bid to be competitive, right? So what I wanted you to do, and no one did it. It's okay. No one actually. If you did submit it, I don't remember seeing it. Okay. So we're sitting here. We're like, okay, how do we do this? So I have an animation here for you. Let's see if I can find it. Fiber optic. Here we go. No. So here's kind of another picture of the same situation, all right? We have building A, building B, 500 feet across, 2,000 feet down. If we're going to lay this fiber optic cable, we can do it along the side of the river. That would be less expensive, wouldn't it? Go back to the note here. Anything that we do on dry ground is cheaper, right? It's $470 a linear foot to lay it there. But if we ever have to go underwater, it's going to be more expensive, right? Right? So there's different ways we can do this, right? Why is it not showing this? So what I'm going to do is I'm going to call this distance, the distance I go along the side of the river, I'm going to call that distance X, right? And this is me this would be laying the wire or the cable on dry ground, right? Because I'm next to the river and I'm laying it along the dry ground. At some point, I have to go across the river, don't I? Like at some point. So one thing I could do is I go all the way to the end, right? And then I could go all the way across. Now that would be smart in terms of that would be the smallest distance that I go underwater. Yes? Just go all the way down and then straight across. I agree. That would be the smallest distance underwater, which would make that cheap, right? But I could do any combination of the two, right? I could go for a certain distance and then cut across, but now I'm going to have a longer distance, right? So the question becomes, how do I do this? Do I do this? Do you think I do that? Do you think that's smart? Just go the whole way across? It's the shortest distance. Would you all agree with that? That is the shortest distance total. Shortest distance between 2 points is a straight line. So that is the shortest distance, but it's all underwater. Here, if I do this, now I'm going less underwater, but it's a longer total distance. And this is the most distance total, but the least underwater. Y'all following me? So let's call this distance from here to here X, and let's call this distance from here to here Y. And I'm going to redraw this picture. So here's my scenario. Here's building B. Here's building A. Let's say that the distance from here to here, we call this X. And let's call the distance from here to here y. Let's talk about the cost of doing this. The cost is going to be the cost for us doing the x part plus the cost for us doing the y part, right? Basically, that's the total cost. It's however much it costs us to lay the cable on the x and then add to that the cable along the y. Well, how much does it cost us to do the cable along the x? Well, the x is on the dry ground, right? How much was the dry ground? 470 per foot,
470.
right? 470 per foot. So shouldn't this be 470x, right? However long x is times 470 is how much it's going to cost me to do that section. Yes? Plus now the cost of doing y, which that's the one underwater, that would be the 710, right? So this would be 710 times y. This is our cost. Y'all understand that? That's our cost. Right now, in order to determine the cost of doing this job, I need to know what x and y are, right? I need to know what x and y are. What you would want to do and what I would want to do in this problem is I would try and figure out how to do this to have the least amount of cost, right? I want to do this as cheap as possible. That way I can make money, right? Because my business, I just don't want to go lay the cable out there just however. I want to do it as cheap as possible. And that way I have a larger profit, right? When I charge the company to do this for them. So right now I'm trying to figure out, I want to see if I can find a minimum for the cost, right? Minimum. What was today about? Finding max and mins, right? Finding the absolute max and min. I'd love to find the minimum of that cost function. The problem with the cost function right now is it contains two variables. It contains x and y. If this was all in terms of x, right? Imagine that this whole right side had nothing but x's in it. Then couldn't I use the method of today? Couldn't I take the derivative of the right-hand side and then set it equal to 0 and then do all that shit with it, right? But I've got x and y. Right now I do. Watch, now it comes the beautiful part. I'm going to use some geometry. I know that this distance from here to here is 500, always, right? Because that's a distance across the river. I also know this distance. Can somebody tell me that distance?
2000, or is it starting on that x?
Yeah, so think about this. X is, right now, X can be anywhere, right? X can be anywhere here. So if I draw a right triangle here, I'm asking you for this distance. That's not
2000 minus
necessarily
x?
it's 2000 minus x. Is that what you said, Red?
Yeah.
Yeah, because we know the distance from here to here is x, right? So from here to here is x. The whole distance is 2000, right? So just imagine, like if this number right here were 500, then this would have to be 1,500, right? It's whatever's left over. Y'all follow me on that? Why am I doing that though? Why in the hell am I doing that? If this is 2000, take away x, then don't I have Pythagorean right here? Don't I have Pythagorean? Look, I have 500 squared. I'm gonna need more room. I have 500 squared plus 2000 minus x squared must equal y squared, right? That's just Pythagorean on that triangle. And now if I take the square root on both sides, I get y, don't I? I get y. Now I didn't do plus or minus, I just did the plus. Why did I do just the plus? Not look at the minus?
You can't have a negative distance or
Yeah,
whatever.
we're talking about a distance of hypotenuse, right? So we know it's positive. But look, everyone, this is great. The cost now is this 470x, right? Plus 710 times y, but we just said y was this, right? y is equal to the square root of, okay, what's 500 squared? Is that 250,000?
Yeah.
Okay, 250,000 plus 2,000 minus x squared. Does anyone have a question on where I got that from? Your boss is going to take you out for beers later, because now you have a cost function that you can find the minimum of. Because, right, this is a function of x. If you can take the derivative of this and set it equal to 0, you will find what x should be to make that the smallest it can possibly be. All right. Do you feel like taking the derivative of that? Yes, you do. Come on, you can do it. Let's take derivative of this. It's not as bad as it looks. Come on, we can do it. Oh, wait, you know what? I forgot something very important. Hold on. Forgot something. Where am I? Where did it go? Oh, it was right here. There we go. Okay. I need to talk about the domain. Okay, because remember, today is about trying to find the absolute maximum of a continuous function on a closed interval, right? We had to have a restriction on x. By looking at this picture, do you have a restriction on the smallest x can be and the biggest x can be? What are they? What's the smallest x could be?
0.
0.
0, right? You can have this scenario, right? And that means you're going all underwater. And then the biggest x could be would be 2,000. And then you're going all the way down and straight across. Now you could argue that you could go past 2,000, but then you're going to get fired, right? Because then you're not thinking at all. I mean, that's just, does that seem completely crazy to say, yeah, we'll go past it and come back, right? So x must be between 0 and 2,000. So I'm going to add that to my little thing here. I have a closed interval between 0 and 2,000. Let's try the derivative. Come on, let's try it. Cost derivative of that. Well, the first one's easy, right? What's the derivative of 470x?
470.
470. Okay, not bad. All right, good, good. All right, what about this 710? It's a constant, right? Comes for the ride. Okay, 710. Okay, times, now chain rule. We have a square root. How do we take derivative of the square root of something?
We can just make it 1/2, can't we? Well, 1
We
over
could.
2 times the
Yeah,
whole
we can do
thing.
1/2. I'm going to stick to the convention we've had here, which is 1 over 2 times the square root of whatever was in there. Right, plus that. Okay, so that's the derivative of the square root part times chain rule. Now you have to do derivative of what's inside, which are two different things, right? Separated by addition. So take the derivative of the 250,000, 0, right? Plus, now look at this one. Isn't that just another little chain rule? Let's not freak out about it. The derivative of this, the 2 would come out first. 2 would come out, and then you have 2,000 minus x, right? To the first power. One more thing. We brought the 2
Yes.
out.
Minus 1.
Yeah, you have to take derivative of the inside of this, which would be -1. So we have to have a -1 here. There it is. By the way, these 2's cancel. So let me see if I can clean this up. 470 plus, let me do it. Well, actually, let me make it a minus. Make it a minus because that -1 right there, I'm just going to bring all the way out in front here. And then the 710, I'm going to push it to the top. So I have 710. Up on top with that, I have the 2,000 minus x. So basically what I did there is I put the 710 and this all together to give me the minus all that on top. And then on the bottom, I still have all that square root crap. There it is. That's my derivative. So what would I now need to do with that? Take that and set it equal to 0 and solve it. Now, I'm not going to have time for that, but that could be done algebraically. You could do that by hand. You would have to combine these into one fraction. You would have to like basically, but I'll show you how to do that algebraically next time. How about we do that? We'll finish it off, but let me back up a step. Okay, let me go back to this function, right? This function right here. We took the derivative of it, right? Because we're going to use the derivative to figure out where the lowest point is. I'm just going to have the computer graph this for us. Okay, I've already got it ready to go here. So I've got the computer is going to graph it. This is the graph of that function. This is it. You're looking at it right now. And I'm only looking between 0 and 2000. I know it's hard to see here, but here's 2000 and here's 0. Look at the graph of that function. It has a local minimum, right? We took the derivative and we were going to set it equal to 0. We ran out of time. If we solve that next class, the solution we should get should be this point down here. Now, I don't remember if I have it. Oh yeah, I already have it solved for us. There it is. That is the point right there. This is the local minimum. And you can see, can you see what the X value is of that point? 1,558. 1,558. So what I can do now, let's go back here. If you go to X equals 1,558. Yeah, I'll bring this up now because I already have the computer doing this for us. So right now, what you're going to see here is the cost. I don't know why I have the cost twice. Let's just look at this top one. Right now, this is it's like $1 million. If I do this right now, okay, if I do this scenario and just go straight from A to B, all underwater, it's going to cost my company $1,463,700 to do it this way. All right. If I move this and I go to this extreme, okay, there, it's going to cost $1,295,000. That's cheaper, isn't it? That's cheaper, but it's not the cheapest. The cheapest is to let X be 1,500. What was it? I forgot. 1,500 something. I forgot what it was. $1,558. So if I let X be 1,558, if I let X be 1,568, $58, whatever it was there. Oh my God, I've screwed things up. So I know you got to go, but I screwed it up, so I'm just going to reopen it. Okay, if I let X be 1,558, I think it was. Somewhere around here. Look at the cost. 1,206,000, right? 206,000 compared to going this way, 295,000. That's roughly a $90,000 difference. $90,000 difference. And all you had to do to make that $90,000 was know a little bit of calculus, right? And you could save that much. So that's just to kind of show you like the power of having something like this. And in fact, if you know how to use a computer, you don't even need the calculus. Like you can just graph that function and find its lowest value with the computer itself. But all right, thank you all for your attention. Do your best to try the problems in 4.1. I know you're going to run into trouble, but at least the first few should go kind of smooth. because they're going to be polynomials and things should be nice. Once the functions get more complicated, yeah, you're going to run into issues. So I expect you to have questions next week. And I'll be happy to go over any of those problems. All right. Any questions? All right. Y'all have a great day, great weekend. Enjoy the nice weather. If you go to Fiesta, enjoy yourselves. All right.
Thank you. You too.
You too, thank you.
I'll be in my office hours later.